Hello, everyone. Welcome to today's webinar. My name is Randy from Element 14, and I'll be your host today. Today's presentation is from Texas Instruments and entitled Enabling Security for IoT Products with Texas Instruments SimpleLink Wi-Fi CC3220. This webinar will be presented by Beatrice Vancombe. Beatrice is currently TI's SimpleLink Wi-Fi Product Marketing Engineer. She joined TI in 2008 as an RF design validation engineer. She's held several positions during her career at TI, including SimpleLink Wi-Fi application engineer and Y-Link Bluetooth application engineer, among others. She holds a Master's of Science in Electrical Engineering from the University of Arizona. At the end of the presentation, there will be a Q&A session. You can ask your questions in the Q&A window below the WebEx screen. So let me hand it over to Beatrice for today's presentation.
Thank you, Randy, and welcome to everybody who is on the webinar. My name is Beatrice Vancombe, and I am the SimpleLink Wi-Fi Product Marketing Engineer. With me today is my colleague, Kobe Lebovich, SimpleLink Wi-Fi Application Engineer. Thank you for joining us. Today, we will explore the security features of the SimpleLink Wi-Fi CC3220 devices and how developers can use them to enable more secure Internet of Things products for everyday users. The number of connected devices in the market is growing exponentially, which means there are more barriers to development than ever before. In a recent study, Bain & Company interviewed more than 170 executives at IoT and analytics solution vendors, and more than 500 looking to deploy these solutions. Their top concerns for implementing IoT solutions included increasing need for enhanced security measures, continued evolution for connectivity standards, limited resources for internal development, and technical limitations such as power consumption. Today, we will focus on those IoT security concerns and the features required to address them. When it comes to security, a good place to start is really by asking yourself three basic questions. What assets am I trying to protect? What do I need to protect those assets against? Where in your system your asset may be exposed to attack. Knowing that, you can start figuring out which set of end-to-end security enablers are needed to best protect your investment. Let's look at it. When it comes to securing cloud-connected products, people often mainly think about the data exchange between the end product and the Wi-Fi access point. But when you examine the system topology end-to-end, there are several additional exposure points to consider. Within the transfer stage from the product to the local router, all the way to the application server controlled by the user at a remote location, and sometimes connected to the original vendor server. Along to the transfer stage, we also have to consider the storage on the end product and the runtime. This is really where the SimpleLink Wi-Fi comes in. This single-chip wireless MCU has a wide range of security features, which will help developers design security measures to take into consideration all these access levels for their product. Let's take a look at how the CC3220 is architected to address these features. The unique architecture of this device and its wide range of built-in security features empower designers to implement several security measures in order to protect their device from unauthorized theft and malicious control. How do we do that? This single chip enclosed architecture reduces the number of possible attack surfaces commonly observed in systems which have the user application MCU externally attached to the Wi-Fi network processor via an interface such as a UART or an SDI. In this particular architecture, the MCU is integrated in the silicon. The two on-chip, yet physically separate execution environment of the user application MCU and the network processor allow for enhanced asset isolation between the developer's IP and the network processor activities. Within this device, there are several built-in security, software security features that aim to reduce the need for any additional external secure components, such as a secure MCU or any other secure element. We have the file system security, which encompasses encryption, access control, file authentication, bundle protection, intrinsic software tamper detection, and also cloning protection. All the encrypted files for the customer IP or data and the consumer data can be securely stored on the stereo flash. The secure files are accessible only by the network processor with the correct access control. We even enable initial secure programming, which is referring to the fact that an image can be encrypted with a secure key before it's loaded on the board. Then a trusted entity can activate the image that is loaded on the device by using one of our tools, UniFlash. This is very useful for factory code protection. We also enable the secure boot to validate the authenticity of any image before its initial runtime. The device also supports 802.11 personal and enterprise security protocol for local segmented networks between the access point and the station. It supports 16 sockets, out of which 6 can be secured with TLS and SSL protocol. The internal HTTPS server runs on top of the TLS sockets with support for client authentication. The unique device identity is an unmodifiable unique 128-bit number that TI stores in the device during production, and it could be used for a connection to a secure server, for instance. The Trusted Root Certificate Catalog is a built-in file provided and signed by TI, which contains a list of known and trusted root certificate authorities. It is used to ensure that the CA is trusted as root of certificate chain for the purpose of TLS and for file signing. The TI root of trust public key is a hardware-based mechanism that allows authenticating TI as its genuine origin of a given content, such as software service pack, the Trusted Root Certificate Catalog, for instance. One of the most important hardware security features in the device are the hardware crypto engine. These engines offload the ARM Cortex-M4 MCU from the complex and time-consuming arithmetic involved in cryptographic algorithms. The hardware crypto engine also are used to enable fast and secure TLS and SSL connection establishment within 200 milliseconds, for instance. This is very important when you're looking at low power consumption. You want fast connection to a network or server. These cryptographic utilities also simplify, sign, and verify operations to validate the authenticity of any new image. Some of the hardware crypto engines are also accessible at the application level, and those crypto engines are AES, DES, SHA, MD5, and CRC. We also have within the hardware embedded feature the device unique key, which is a hardware-based, readable only by the network processor. It is used for cloning protection mechanism. We also support the debug security, which enable blocking access to the debug capabilities such as the attack interface and file access from external tool once the device has been released to production, for instance. Now that we have looked at several of these features, I want to show you this figure. It shows a high-level diagram of the CC3220 embedded security features that I just explained earlier, in the application with respect to different access level from a potential attacker. Let's see how their combination will enable and assist designers to implement security measures for their end product and reduce the security risk within their intended application. The end product can be any IoT connected device. In this example, we're considering, for instance, a smart thermostat from a great company which uses the CC3220 or the CC3220 SF on their PCB. Okay? Let's take one particular use case if we consider the over-the-air update, which is a remote software update on the product after its deployment to everyday end user. The first step in the over-the-air update is important to establish a secure local area network connection. This can be done by leveraging the embedded network processor personal and enterprise security feature, such as the WPA, WPA2. In the local network, we use the hardware crypto engine that are uploading the host. Then the next step is important to establish connection to the internet to the application server while leveraging the TLS and SSL protocol with hardware crypto engine as fast as 200 milliseconds. This is very important because some connection could be longer if you're not using hardware crypto engine, and it's very useful for systems that look into power saving, for instance. The TLS and SSL are part of the network processor within the DSP socket layer. It's important also to prevent any potential man-in-the-middle attack with the application where the application server has to be authenticated as a genuine server against the CC3220 Trusted Certificate Catalog, which contains the list of known and trusted root certificate authorities. The CC3220 must also authenticate itself as the genuine origin of any given content. In this case, we're leveraging the TI roots of trust public key. All of this is handled by the network processor. Then the next step, the CC3220 uses its unique device identity in order to be validated and approved by the application server. This unique key is stored inside the device, and it could also be read by it could also be utilized by the application server to authenticate the device. This prevents any unauthorized device from accessing the application server and getting the software update. Imagine, for instance, that you deliver your secret code to the competition because it didn't validate the product which was requesting the software update before the software update actually starts. Once this validation is done, the secure content delivery allows retrieval of the software image from the vendor application server to the intended device. The secure content delivery then enables the exchange of confidential content to the device. That content is decrypted by the device, and no entity along the way carries the same knowledge to decipher it. That's what we mean by the secure content delivery, because it lets the user program content that has been encrypted by the remote device, and it is decrypted on the fly inside the network processor. The private key used for the process is kept inaccessible inside the SimpleLink network subsystem with no access to the host. Thus, it allows secure content transfer on even an unsecure network. When the new file bundle from the server are decrypted on the network processor and stored in the serial flash, it is recommended to store them as encrypted image to prevent any physical attack from reading the application code. The device unique key is leveraged by the intrinsic cloning protection mechanism. It ensures that the file system is only readable by the network processor, which first wrote that image to the serial flash. In other words, any encrypted image on the serial flash is only readable by that network processor it was first attached to. So the code that was delivered from the vendor and downloaded onto the serial flash is again encrypted on the serial flash by the network processor, and it can only be read by that network processor. Once the over-the-air of the new image is complete, the CC3220 will restart with the new image. But first, the secure boot will validate the integrity and authenticity of the binary. If this image is not valid, the device will default to the previously known good image. This is done in order to protect any attempt to hijack the device with malicious software, for instance. During this over-the-air update use case, we've covered several security features that were leveraged. These are merely building blocks that developers can leverage when they want to design securely connected IoT products. And they can get all of these features when they select the CC3220 devices, the single-chip wireless MCU devices, and all of these are embedded within our device. I would like to take another example. For instance, at another intrinsic feature called the cloning protection. This feature is enabled by default to protect the content of the serial flash on any particular product. The file system, including the developer's IP, are encrypted using a unique key per device, and we also leverage the AES-128 when we want to encrypt the files and store them on the serial flash. Any attempt to corrupt the information on the serial flash, or if the serial flash is even moved from one particular device from vendor A, for instance, to another product from vendor B, for instance, is really futile because the serial flash on the product from vendor B will not be readable by the other network processor. During the boot process, the network processor will notice the difference in the file system, and it will result in a security violation detected, and the CC3220 device will enter a lock state. This is the cloning protection, which is intrinsic to the CC3200 devices. I would like to show you another feature, such as the software tamper detection, which constantly monitor the use of files and detect attempts to tamper the file system without any proper authorization. Note that the serial flash, the files stored in the serial flash can actually be potentially attacked from several layers in the network. The remote attacks represent the vast majority of security breaches. The secure files can be encrypted, or they can be encrypted and authenticated. And any of these files will require the right access token in order to be read. And they are only read by the network processor. If the secure file tampering has been detected, a security alert is issued to the MCU. The developer can choose to report and implement, developer can choose to report those alerts to the server, and it can also choose to implement security measure based on those notifications, which we'll recommend. Once the security, there is a security alert counter that is set for every attempt failure, and we have a threshold currently set at 15. Once the security counter alert reaches that threshold, the device will enter also a lock state. And only a manual force reset will enable the device to be unlocked. And when it's done, the device will actually reset to the developer's factory default image. Now, we've addressed several use cases here, showing how all of the built-in security features of the CC3200 are leveraged at numerous access levels. It's important, therefore, to understand that all of these features are part of the CC3200, and they can be leveraged by developers to implement the security features that they need. The developers have the luxury to select which features they want enabled, and we recommend leveraging all of them. As a summary, our world is evolving with the growth of wirelessly connected products. Every connected product needs security measures to prevent unauthorized attacks and accesses. Because Wi-Fi is the default technology which enables all products to be part of the Internet of Things, TI has invested in Wi-Fi devices that provide developers with tools to help address those security challenges. Beyond the local network security, the SimpleLink Wi-Fi CC3220 wireless MCU incorporates those several security features to help you implement the appropriate measures for your IoT connected products to ultimately protect your own IP during the development and after mass production release, as well as the protection of your end user data and identity that are stored on the product and that are transferred on the network during runtime. We invite you to visit our SimpleLink Wi-Fi website. And for specific documents, we do recommend that you visit our product page specifically on the CC3220 device, that you visit the security, read the security app note that we have posted online. We also have available several tools to evaluate several of the security features in the CC3220 Launchpad. And during your evaluation and your development, if you have any questions, you can reach out to us and also log into our TI E2E support community to ask any questions that you may wish. Thank you. And I will open the session for any questions that you may have.
So we have two questions, actually three already. What is the minimum size of the external flash?
The minimum size of the serial flash that we recommend today is 16 megabits. And our device, 16 megabytes actually, right? 16 megabytes. But in our device, because we recommend also space for the over-the-air update, we recommend the use of 32 megabytes.
The next question is, can the serial flash be used for other user purposes such as backlog or more?
When you're referring to other purposes such as backlog, what exactly are you specifically referring to? Okay, so the serial flash, the network processor writes to the serial flash, but we also have space available for the developers to write their files onto the serial flash. So there is space available on the serial flash for the developers' file system.
The next question is there a module version of the CC3220?
Yes, we have a module version of the CC3220 S and the SF, and they are actually available today online for sampling. They will be released to market by the end of June. You can visit the ti.com/product/CC3220 mod.
Is there a launch pad planned or available? In that case, is support from Energia plan for this CC3220 as it is already done with the CC3200?
The development, Energia is supported today on CC3200. This is something that the team is potentially considering in the future, but at the current time, it's not in the short-term plan to support Energia on the CC3220 launchpad. But we do provide several tools online, and also anybody can actually enable that support for Energia on the CC3220 launchpad.
Okay, the next question is the module version pin compatible with the CC3200 mod?
Yes, the module for the CC3220 mod is pin compatible with the CC3200 mod.
Okay, the next question is, what functions have the Wi-Fi module embedded? Can it run as a Wi-Fi access point to configure it directly from a smartphone, and as a Wi-Fi client to connect to an external server on the internet?
So the CC3220, there are several Wi-Fi options that actually enable in the device. It can run as, let me show you here. Okay. It can run as a station. It can also run as an access point. And you can connect to it also from your smartphone.
It supports the provisioning through an AP mode, if this is the question, or connecting it to a network.
The next question, how many devices can be connected through the Wi-Fi?
When the device is in access point mode, we can accept up to 4 stations connected to the device.
As an access point, does it need more RAM or external flash?
No, as an access point, it does not need more RAM or external flash. The device actually has an integrated 256 kilobytes of RAM for the CC3220S device, and for the CC3220SF, it has 256 kilobytes of RAM plus an additional integrated 1 megabyte executable in-place flash.
What is the S flash size of the CC3200 mod?
You asking what is the stereo flash size of the CC3220 mod? Is that the correct question?
Yes, it is.
Okay. The module has 32 megabyte external serial flash attached to the device.
Next question, what is the maximum speed that the Wi-Fi can support?
Our device support 802.11. We work at 802.11 BGN for 2.4 gigahertz. We have measured and observed throughput up to 16 megabits per second.
UDP.
And this throughput to observe is usually sufficient for IoT connected products. Oh, it's 32.
Are there any more questions?
Well, actually, one thing that I wanted to clarify on the size of the external serial flash for the module, it's actually 32 megabits for the serial flash, and this is a recommendation that we have, especially when you're looking also at enabling over-the-air updates for the devices. But it can accommodate even higher. I think it's up to 128 if anybody would like to add additional, have additional space on the serial flash.
Are there any more questions? Okay, next question. Does it support an ARP static table?
Can you give us 1 second? We'll be right back. When the device is an access point, if we're referring to the ARP management of the IP address, when the device is in AP mode, then we can also allocate the different IP address to various stations. I have to check if the ARP table can be configured for any of our customer and get back to you on this one.
In which languages can it be programmed? C, C++, Python?
provider, and it's only it can be extended later.
The device with SDK that are released and provided, the device can be programmed in C.
What kind of RTOS does the CC3220 use?
Can you repeat the question again, Randy, please?
Sure. What kind of RTOS does the CC3220 use?
Oh, okay. The CC3220 would work with FreeRTOS or TI-RTOS, but it could also be programmed for non-OS.
Are there any more questions? Yes, we have one more. Does it have analog inputs to connect sensors?
Yes, the device has several inputs. We do for the peripheral. If you could give me 1 second, I could bring up the architecture for the device. We have several peripheral. We actually support the I2S, I2C. We also support 4 channels, 12-bit ADC input. We have support for peripherals such as the UART and SPI.
Is it possible to increase the RAM size externally?
You mean increase the 256 kilobytes of internal RAM, add an external RAM?
Yes.
No, currently it's not possible. The code would be running on the internal RAM to the device. And we find that for some applications this is actually sufficient, but we've actually encountered the need for some customers to have more internal executable environment. This is the reason why we have the optional CC3220 SF, which provides the 256 kilobytes of RAM plus the internal 1 megabyte executable in Blitz Flash for larger applications.
Does it support FPGA?
No, in this particular case, no, we do not support the FPGA.
Support only chip level.
Does the chip support Apple HomeKit?
Yes, we do support the Apple HomeKit. And if I may, Randy, since we have enough time, can I show the introduction with the thread of questions? I could show a short introduction to additional, pretty much the overall architecture of the device, irrespective of just the security features. Can we do that?
Sure, we have plenty of time.
Okay, so let me switch to that presentation. Okay. All right. So given the thread of questions that we've seen, that we've received, and I appreciate the interest, we wanted to focus the topic on the security feature, but I want to take a moment to show you more the internal architecture of the CC3220 devices and what it supports. So if we start by looking at mainly the network processor, for instance, the network processor offloads its intention is to offload any networking and also all of the internal related tasks from the application MCU. We do support 802.11bgn at 2.4 gigahertz. We support AP mode, we support station mode, we support AP mode, and when we are in AP mode, we support up to 4 stations. We also support Wi-Fi Direct. The Wi-Fi security mechanism that we support are WEP, WPA2, and WPA. WPA2 for personal and enterprise connections. The WPA2 is actually the recommended security that we suggest to all of our customers. We support WEP only. Okay, apologies there. I'm going to take a moment here because I had paused to bring in this additional content to the team. Can everybody see the presentation now with the internal architecture of the device? Perfect. Given the different questions, I wanted to show you more information with regards to the architecture of the device. The network processor aim is to offload all networking and internet-related tasks from the application MCU. We do support 802.11bgn at 2.4 gigahertz, and we also support several modes for the Wi-Fi such as station, AP mode, and when we are in AP, we can accept up to 4 stations. We also support Wi-Fi Direct. For the Wi-Fi security, we support the WEP, WPA, and WPA2 for personal and enterprise security. WPA2 is the recommended networking security that CI suggests. WEP is only supported for legacy compliance. We do support several provisioning options such as AP mode, the TI proprietary smart config, and WPS. We also do support the Apple WAC method of provisioning, in which case you need to add the Apple MFI chip to your design. The throughput will support up to 16 megabits per second for UDP and 13 megabits per second for TCP. It has built-in power management with integrated DC-to-DC, and will support the wide input supply voltage from 2.1 to 3.6 volts, or the pre-regulated 1.85. The integrated power management enables the support for shutdown mode at 1 microamp, hibernate at 4.5 microamp. For both shutdown and hibernate, we disconnect from the network, and we have to reconnect to the network once the device wakes up. We also support the low power deep sleep mode, which consumes about 135 microamp. During the low power deep sleep, we stay connected to the network. And we also support the RX beacon listen mode at 30 which consumes about 37 milliamps. This is when we wake up every beacon, which is about every 102 milliseconds or every BCM as set by the access point, to listen to the incoming beacon from the access point. For some of the integrated internet and application protocol, we support the embedded web server HTTPS. We do support IPv4 and IPv6. And IPv6 is one of the requirements, actually, in order to be able to support the HomeKit for Apple. The device supports up to 16 sockets, and 6 of which can be secure. We have the integrated powerful crypto engine, which are leveraged by the network processor, and some of those engines, as was mentioned, are also accessible to the application MCU. If we look at also the feature for the device for the application MCU, this is a physically separate MCU and memory completely dedicated to the user application. We have several peripherals, as you've seen listed there, the SPI, UART, I2C, I2S, 8-bit parallel interface for the camera, and 4 channels, 12-bit ADC input. We do support the no OS or TI or FreeRTOS for the OS running on the device. There are several peripherals that are available up to 27 I/O, which with flexible muxing options. We do provide a PinMux tool in order to allow you to aid the developers to program the peripherals. And as part of the reset of enhanced features, we have several file system security features which we just covered for the first part of the webinar in order to enable the developers within this single chip architecture to implement measures to protect their IP, their data, and the end user data. With all the security integrated and also the support for the IPv6, we have been compliant to the HomeKit technology, and we actually have a HomeKit plugin software which is available for download on our website, and that one has passed the Apple HomeKit certification. That plugin is downloadable and installable on top of our initial base SDK. And we do also provide an example for over-the-air And when we look at these devices, this is the simplification really of the architecture. It's important to notice that the key point about these devices is that all of the embedded power management is done in order to enable the CC3220 device to run for several years on 2AA batteries. We do support several layers of security features as we've just outlined, and the Wi-Fi stack within the device has received the Wi-Fi Alliance certification. And this Wi-Fi Alliance certification can actually be leveraged by any device. It's actually transferable, meaning if you design your end product with the CC3200, you can transfer the Wi-Fi Alliance certification and have the logo affixed on your end product. For any device, for any product, we offer the wireless microcontroller, the system on chip that have for which I've shown the architecture. And these can be used pretty much as the main MCU in any system. And these devices have the internal MCU for the user application, along with the network processor, which manages all the Wi-Fi connectivity. For any customer that has a legacy MCU in the system, and they would like to continue using that MCU, for instance, we also do offer the CC3120, which is mainly the Wi-Fi network processor, which allows connection to any external MCU. And all of these solutions come in a certified QFN, in the Wi-Fi. All of these solutions have the Wi-Fi Alliance certification, and they come in a QFN package IC. We also provide modules for both of them. And the modules have the regulatory certification across the world for FCC for the U.S., and that are leveraged across in several countries in the world, and also IC for Industry Canada, CE or RED for Europe, TELEC for Japan, and SRRC for China. It allows application worldwide. The devices are pin-to-pin compatible, and the modules are pin-to-pin compatible, respectively. This is pretty much some of the features that I wanted to show you. And in highlight, I want to show you the main differences between the first generation of our devices and the second generation. This table gives you a nice summary. If once you visit our main page, SimpleLink Wi-Fi, you will come across the first generation 31 and 3200, and the second generation, which was the focus of the webinar today, the CC3220. And you will see that there have been several improvements that have been done between the first generation and the second generation. Particularly, the larger on-chip memory with the integration of the 1 megabyte on top of the 256 kilobytes of RAM. The support for 4 stations when we're in AP mode. And most importantly, the embedded IP and file system security features that we've addressed today during the call. This really brings security to the forefront because it's important as we develop IoT connected device to be able to protect your own development, your own efforts. And on top of that, be able to implement measures to protect your end user identity and data. We are compliant with, we support IPv6 and the security measure also allow us to be compliant with the HomeKit communication protocol. And these devices, for several low power profile, we also have seen improvement of more than 30% in battery life, for battery powered end applications. And we have enhanced the provisioning offering with the support of the WAP, which is the Apple proprietary network, and also several enhancements in the TI proprietary smart config provisioning option. With that, I would like to see if there are any additional questions with regards to the architecture for the CC3220 device.
Are there any more questions? Well, if you have any more questions, you can visit the webinar page in enter them in the comment section, and we'll be happy to answer them after the webinar. So I think that today concludes this webinar. I'd like to thank Beatrice for delivering really an informative presentation. And I'd also like to thank everyone who has taken the time out of their busy day or evening to attend. Finally, I'd like to remind everyone that Element 14 is currently enrolling for our road tests, the SimpleLink Wi-Fi 3220X wireless MCU Launchpad. Please visit the webinar page, which has a link to the road test, or go directly to the road test group itself on the community to sign up. So thank you for everyone, and have a great day or evening.